Hi there. We're going to start talking about homomorphisms, isomorphisms, and automorphisms. So just a little refresher here. A homomorphism from a group G, and then we'll have the operation be this asterisk, to a group H where we have diamond as its operation, is just a function phi from G to H such that phi of this x and then that asterisk y equals phi of x, then the diamond phi of y. So notice the x star y we're talking in G, but then the phi of x diamond phi of y we're talking in H, our elements. So this should happen for all x, y in G. And then a special type of homomorphism is an isomorphism. So an isomorphism from a group G with that asterisk to a group H with that diamond is a homomorphism, and then we'll call this one F from G to H, such that F is a bijection. So now what does it mean to be a bijection? We have that one-to-one and onto going on. Okay? So now we're ready to tackle automorphisms. So what exactly is an automorphism? An automorphism is just an isomorphism from G to G, so basically back to itself. So with that in mind, what's actually happening here? Well, what we're looking at is you have this set, let's say we'll draw a Venn diagram of all homomorphisms. And by the way, this lies in another set of all functions. Not saying the size of these are actually to scale, obviously. So what happens then? Well, inside the homomorphisms, we have a smaller box or a smaller little blob here, and that would be the isomorphisms. So a very special type of homomorphism is an isomorphism. And then on top of that, even more so, you have another smaller blob. And so a special type of isomorphism, when we send it the isomorphism from a group to itself, is an automorphism. So if you do have an automorphism, you do have an isomorphism, and if you do have an isomorphism, you do have a homomorphism. But you can't reverse the order. In fact, if we go homomorphisms, isomorphism, you might not even have that. In isomorphisms, you might not even be mapping to the same group. So right away you would know that it's not an automorphism. So we're going to try and explore some of these topics in just a different route as to what's going on. And so if you have any questions along the way, just let me know in the chat box, and I'll attempt to answer these as best I can. So let's get started here with some questions. So determine if phi from basically our 2x2 matrices with non-zero determinant into the multiplicative group of real numbers given by this phi of A equals the determinant of A is a homomorphism. So if we want to determine if this is a homomorphism, what do we have to check? Well, if you go back a page, so the real question here is, does phi of AB equal, and I'll put a question mark up top, phi of A, phi of B, for all A, B in those that set of 2x2 matrices. Okay, so I'm not sure how familiar we are with this. Just so we recall, if you have A, B, C, and D, what's the determinant look like? So this is a special notation for determinant, by the way. That would equal AD minus BC. Okay, and you can kind of check. There's actually a property, and if you need to see it, just let me know. But what we have at the end of the day, we have a nice little factoid here that the determinant of the multiplication of two matrices always equals the determinant of A times the determinant of B. And you can just set any two matrices in, and you can see that this property holds. So with that in mind, let's take a look at if this actually works. So our check for a homomorphism, how does it go? So we'll go phi of AB, and once again I'm assuming AB, so A comma B are elements of our matrix group there. Okay, so what actually happens then? Well, this should equal the determinant of AB, which we saw up above, just recalling a property of determinants. This equals the determinant of A times the determinant of B. Well, wait a second. Determinant of A, that's just phi of A. And the determinant of B is just phi of B. And we have a result. So phi is a homomorphism. So now the next question kind of comes after you have homomorphism. Can we go any further? So the question that I'll follow that up with is phi an isomorphism. Okay, so answering this question, actually it isn't too bad. So you have to check one-to-one and onto, and we could start to try with the general case, but I always say try with some examples, and it does take some practice to kind of get to the right examples here. But take a look at, if you notice, phi of, let's say, the matrix, which is just the identity matrix. Okay. Notice that would equal, just using our determinant properties, 1 times 1 minus 0 times 0, so that's just equal to 1. And if you look at phi of, I don't have to use anything special here, I'll just use negative ones in both of those positions. That also equals 1. But those two matrices are not equal. Since they're not equal, that means this function is not one-to-one. So is phi an isomorphism? The answer is no. So you just have a homomorphism, and that's all we can't go any further than that. So keep in mind one thing, this isn't a formal write-up, but you're just seeing some sketch work here. So if you wanted to see a formal write-up, basically I'd take, I'll star this line here. On this starred line, I'd have some build-up. So I'd be like, let A and B be elements of our GL2R here, and then I'd write the word then. Phi of A, B equals all this line, and just finish it with a period, hence phi is a homomorphism, and you're done. But so just because what you're seeing here is a sketch doesn't mean it's the final write-up. This is just the rough draft in terms of figuring out an answer, and then we have to do a rewrite in order to actually submit something. So keep that in mind when actually writing these up as well. Alright, let's take a look at another problem. So determine if the integers under addition is isomorphic to the rationals under multiplication. There's actually going to be a couple ways to approach this. I'm going to focus, say we don't know quite as much right away in terms of how these things work. So in terms of the isomorphism, we need a function to be one-to-one and onto. The other thing too, we have identities so that we got to work with. The identity equals 0 here, and in this case the identity equals 1. Okay. The other thing too though that we can take note of is the integers is a cyclic group generated by that element 1. Okay, so we can build to all integers just from based upon that one value. Now, how do we move forward here? Well, let's see. Let's just assume there exists a homomorphism. And we'll call it, pick your favorite Greek letter that we want. We'll call it phi, and we'll take it from the integers to those rational numbers. Okay. Since the integers are completely determined by this element here, we can see where that thing maps and get an idea as to what's going to happen in the rational numbers. Oh, and let me just to indicate this, that multiplication here means we're leaving out 0. So I should probably indicate that q minus this element 0. Otherwise it wouldn't be a group in the first place. So where do we go from here? Well, let's see what happens with phi of 1. Well, we know it's mapping into the rational numbers a over b. Okay, and then we can start to see, well, what's going to happen with this? Well, phi of, let's say 2. Well, this should equal phi of 1 plus 1. Oh, sorry about that. Phi of 1, first I'll write it this way. And if this were to be a homomorphism, that means it has to be phi of 1 multiplied by phi of 1. So that means this would be a over b, the quantity squared. In a similar manner, we could find phi of 3 equals a over b, the quantity cubed, right? And phi of, let's say n, should equal a over b raised to the n. Right? So any questions on that? Well, if we have this piece, what does that mean we have to do? Let's say we want, well, notice we can always write, if we have phi of n equals a over b to the n, let's say we have, so we're in the rational numbers, let's say we want a number, so let's put it this way. There's a few different routes to take here. Can we map to 2? Right? So just kind of seeing how we build this, is it possible for us to map to, say, this element 2? Well, yeah. Okay, so what we have to do is we need a over b raised to the n to equal 2 for some n in our integers. Well, there's really only a couple of possibilities here. Okay, and if that's the case, so what happens here? Well, notice if n is 3 or 4 or 5 or any other number other than 1 or -1, what happens? Well, when you try and generate this element 2, you'd have a root over here, and we know that a root would be giving us an irrational number, and we can't have that. We need a over b to be an element of the rational numbers. So we've run into a problem now. Okay, so that means this would imply n equals 1 and a over b equals 2. right? And we can reduce this fraction. So one thing going back here, we can assume that this is in lowest terms and all that jazz. Oh, I say 1. Actually, I should be careful. It should be plus or minus 1. So that means either one of two scenarios occur. So either you have, if a over b equals 2, so either you have a over b equaling 2, or in the case that n is, a over b equals 2, or b over a equals 2. If you have the case of b over a equaling 2, that means, and so here's your two cases. You have phi of 1 equals 2, or phi of negative 1 equals 2. So wait a second though, when we go back to this, our phi to n, that implies that phi of n equals 2 to the n. But the problem with this is it's not on 2. Right? You aren't going to hit every rational number with this. Now, you might see that we've been working with just 2 as our magical number. Was there anything else we're working with? Could we have chosen 3? Could we have chosen 4? Oh, of course we can. We can choose all sorts of different numbers. Our argument would just be slightly different for each case. So this just gives you an idea if you had no idea where to start. Now, if you really wanted to have a good start at this, the best approach is to understand what happens if we have a cyclic group. Okay, so if you have a cyclic group and you're looking for an isomorphism, well, you need to map. In order for that to occur, you would need to have another isomorphism. So that's probably our best approach. It's a much quicker approach, and you don't really have much work to do. You know that the integers is cyclic, so you're good there. You know the rationals is not cyclic, and so there cannot exist such an isomorphism. So since we had our not on 2 though, we showed it. That was the hard way. Not saying it's the only way. There's actually plenty of other approaches. Now, by the way though, is this a homomorphism? Yeah, this would be an example. We could kind of show that this would hold up and be a homomorphism. So homomorphism, but not an isomorphism. But yeah, keep in mind though, if you have that this is cyclic, you need that this has to be cyclic. And so your shortest proof and the best approach is to just use the fact that whether or not it's cyclic. Okay. All right. Moving forward to a harder one. Oh, not just yet. So in this case, let R be in that multiplicative group of integers modulo n, and we want to determine if the mapping alpha from Zn to Zn defined by this alpha s equals s times R mod n for all s in that Zn is an automorphism of Zn. Okay, so taking a look at this, how do we actually approach such a problem? Well, we need to see if it's an isomorphism. Essentially, we're going from Zn to Zn already, so you're just seeing if this is an isomorphism. Okay, keeping that in mind, how do we approach this? Well, there's going to be one little tidbit. If this happens, this R is in Zn, what actually occurs? Well, that means that the GCD of R and N has to equal 1. And what does that mean? Well, that means there exists x and y in the integers such that Rx plus ny equals 1. Or another way to think of this, you can think of it as Rx minus 1 is equal to negative ny. And why is that important? Well, that implies that Rx is congruent to 1 mod n. Okay, so we have Rx is congruent to 1 mod n. What are we going to do now? Well, let's try and work and see if we can figure out if this is first a homomorphism and then kind of work with that. And so that was just working with what R does for us. Okay, so let's check the homomorphism part first. So in that case, we want to look at alpha s times t. By the way, we'll say s and t are elements of Zn. In this case too, we want to notice that this is the additive group. So this Z right here, Zn and Zn, this is the additive group. So we're adding things up. So, and just to kind of indicate that a little bit better, I just wrote s times t. So you can see that a little bit better. I'll write plus so we can notice that difference in between there. So what does this equal? Well, this equals s plus t times r. Now I could put the mod n, but I'm just going to continue this. And so this is equivalent to sr plus rtr mod n. And I'd like to do them in one line, but it's not necessary. If you wanted to do it, you could do it on the other line, and you can check out that that equals alpha of s is just sr plus alpha of t is tr. And so notice I used plus this time because that's our operation, since we have an additive operator. Okay, so now where do we go from here? Well, we have a homomorphism, right? That's our so alpha is a homomorphism. So we're good on that part. Now we need to do a couple other checks. So we need one-to-one. Okay, so in order to do that, assume, and I'll use s and t again, alpha of s equals alpha of t. Technically I should use something maybe a little bit different, but at the end of the day we'll get at the same result. So what does this mean? That means that SR is equivalent to ST mod n. No, sorry, not ST. TR. Sorry about that. Okay, well, where can we go to actually solve this? Well, we actually have a nice piece that we mentioned before. Since the GCD of n and r equals 1, you have that there exists an x such that r times x is congruent to y mod n. That's just from our linear combinations. We talked about that kind of at the beginning of the semester. So now what we can do, this implies that SRX is equivalent to TRX mod n. And I'll move parentheses in there. Now, what does that mean? Well, Rx is 1, so you have S times 1 and T times 1, so you get S is congruent to T mod n, meaning they're the same value. Now, technically, X, you got to think about it. It could be in the equivalence class. It could be something like -5 or whatever. It depends upon R. But as long as we're talking in the equivalence classes, we're going mod n. We're fine. We're good to go. So you have S congruent to T mod n, hence alpha is 1-to-1. Okay. Now, moving forward from here, we need onto is our next piece. So for onto, we got to map to something. So let's let, we haven't used y. Let y be an element of Zn. We want to find something that maps to y, right? So does there exist, we'll call it Q, such that alpha of Q equals y. Well, think about this. If we have alpha of Q, so our work will be different than our write-up, by the way. So alpha of Q, what happens? Well, that means we would have Q times R. So, and that should equal y. Well, we want to solve for Q, essentially, mod n. So our work will actually look like this. When we go through, we multiply both sides by x. QRx is equivalent to yx mod n. Well, what does that mean? That means Q is equivalent to yx mod n. Okay, why is that important? Well, and I'm also going to use the fact that we have a abelian here for our nice little group. So that means if you're actually writing this up, what you have, and it'll look like magic when you actually write it up, but we've ended up solving for it. Alpha of yx equals, notice we have yxr, which is equivalent to yrx. Right? We really don't need that extra step because we do know it's abelian, but just trying to emphasize that. And we know Rx is equivalent to 1, which is, so this is equivalent, whoops. Oh, let's drop that back down. Oh, let's drop that back down one more time. Sorry about that. Which is equivalent to, let me try and erase that. There we go. So that's equivalent to y mod n. So alpha is on 2. And there we go. So formal write-up would look a little bit different, but now you see all the components in working that problem out. What do we need to do, right? All right, moving forward to the next bit. So this can be a little bit of a challenge sometimes. If a group G is isomorphic to a group H, then determine if the automorphism group of G is isomorphic to the automorphism group of H. Okay, so you might recognize this one. So first off, let's say we have this blob, and this is G, and it maps into this other blob, and this is H. Well, if this is phi, and this is our isomorphism, right? That basically is telling us that these two things are the same. Another thing to think about is that if it's an isomorphism, that means it's 1-to-1 and onto, meaning a bijection, meaning an inverse exists. Okay, so we can define that inverse. And then you have some results here. Phi inverse is also an isomorphism. Okay, so that's a nice result we're going to make use of. So now, aught G. What is this? Well, the elements are isomorphisms from G to G. Aught H the elements are isomorphisms from H to H. Okay? Now, okay, what's happening here? Well, we want to take something in aught G and map it over here. We have to find something first in aught G, and we'll give something, and then we got to turn it into something in H. Okay? So, if we take some element alpha, we can't say alpha over an H, right? That doesn't quite work for us, okay? Because even though these two are isomorphic, it's not the same group necessarily. Well, they behave the same and all that stuff, but they're not listed as the elements being identical in terms of, for example, if you look at the fourth roots of unity under multiplication and Z4, right? Those two are isomorphic, but I'm using negative I1 and negative 1 for the fourth roots of unity, and I use 0, 1, 2, 3 as the elements of Z4. So even though they might be isomorphic, I'm using different symbols essentially. So we have to figure out what will actually turn this into an automorphism in H. Now notice I'm just saying this says determine if they're isomorphic. I'm saying if this were to happen, that's what we have to do. So the key thing with if you're going to prove it, you usually look, can I use something in the statement? So we have in the original part, we have G is isomorphic to a group H. That's what we called phi that isomorphism. So let's see how this works. Okay, so we probably want to use phi. So aught G, remember, alpha maps G into G. If it's to be in the automorphism group of G, alpha has to map some G into G. Okay, how do we send that into aught H? Well, let's think about that. We want to start in H. So that means on this right hand side, if we want to start in H, looking back at our map over here, we want to start with phi inverse, because phi inverse starts in H. And I know going on the right that may seem confusing, but remember our first move is the function on the right. So our phi inverse, we're starting in H and we're mapping into G. Okay. Now what does alpha do? Alpha takes G into G, so we're still into G, but we want to map back into H. And if you notice, if we take phi, we're mapping right back into H. So we'll finish with phi. So basically what's happened is you've taken this phi inverse over here, and then once we're in G, we take alpha and it just loops right back around and stays in G. Right? Okay. And so this map, we started in H, went across, did a maneuver, an automorphism in G, and then we moved back with that isomorphism back to H. So notice we started in H, finished in H. So this phi alpha, phi inverse, but notice when we read this, we start with this phi inverse, then alpha, then phi. That's our function composition. This maps H to H, which is good, right? So now we have to do a couple things. We need to show that this, so is this an automorphism? Right? Well, in order to do that, we have to show that that's an automorphism, and we'll have to show that this map, so two parts. Tau of alpha, well actually we can kind of get through this, equal to phi of alpha, or phi alpha phi inverse. So, and I should write, essentially, is this a homomorphism? Right, and then the other part is phi alpha phi inverse an automorphism. From H to H. So that's about the well-defined part. Okay, so hopefully you see that first off we have phi starting in H, or phi inverse is our first element, and we're starting in H. So in order to see that, we'll do the automorphism, we'll do the well-defined part first, and then I'll actually erase it and kind of go through. So first off, let X and Y be elements of H. Right? So now I'm talking about elements in H. We'll try and show that this is an automorphism. And consider phi alpha phi inverse of xy. And I should be a little more careful. What is our operation here? Well, these are functions, right? Since we're talking automorphism, or permutations, I should say. So phi composed with alpha composed with phi inverse. Hopefully that looks a little bit more familiar, of xy. So now we can start breaking this down piece by piece. Well, this means we have phi composed with alpha, and then the other component, though, we know phi inverse. Phi inverse is an isomorphism, so that means this is a homomorphism, right? So we can break this apart into phi inverse of x, and then phi inverse of y. Okay? Well, now, this is an element of G. This is an element of G, right? Because we map back over here. And we know that alpha happens to be an automorphism because it lies in G. So that means that this equals, we have phi composed with, in this case we'll have alpha composed with phi inverse of x, and then let me write it that way, times alpha composed with phi inverse of x. And technically I should be writing this down, I'm just limited on space, and then I'll actually erase this part in a second. And so now we know that this is an H, and, oh, I'm sorry, I should have written y in the last component there. And this element has to be an H, because alpha, or, oh, I'm sorry, not an H, in G, my apologies. So both of these are in G. Alpha actually maps G back to itself. So now we have, with the phi on the next part, that's also an isomorphism. So we can break this up into two different parts. So this equals phi composed with alpha composed with phi inverse of x, and then times the phi composed with alpha composed with phi inverse of y. Okay? So, and so there was a question along the way. Can we use the fact that they're an isomorphism to assume it's a homomorphism? We're going to actually show it, just to make sure that this actually is a homomorphism. So you don't want to necessarily assume. You do have the isomorphism, but we have three components going together, and that's the whole crux of this proof, is essentially showing that result, showing it's a homomorphism, and then also showing, essentially you're showing composition of isomorphisms is also an isomorphism, is what you're trying to show in that case. Now, if you found that result, I think kudos, and keep on going and using it, right? Basically you're showing, that would be the case of showing a transitive property, kind of showing one thing's isomorphic to another, and that's isomorphic to another. Does the transitive property hold? That might be coming soon to a homework near you, by the way. Just keep that in mind. But so at this point, what we're showing right now isn't the homomorphism, we're showing well-defined. And so is this actually an automorphism? Well, notice what we've shown is this thing here is a homomorphism. Okay, just getting in the habit of it. Now, for the one-to-one and onto, you actually did have homework problems on this. So each component here is one-to-one and onto. And so that part I will let slide. So the composition of functions are one-to-one and onto as well. So moving back though, this is just showing that well-defined. So meaning that we are mapping to something in the automorphisms of H. So what that tells us with all these pieces, that tells us that phi alpha, phi inverse, and remember we should be reading it, phi inverse alpha and phi is, well, let me just write it this way, is an element of odd H. Okay, so it is well defined in terms of we are having a function work out. Okay, so now let's look at the homomorphism part. And so as you mentioned though, can't we just assume it? Well, if you can show in general that if we use composition of isomorphisms we get another homomorphism, then you've actually generalized the result and you can use it over and over again where you don't have to check these three, but you'd have to show that result. Until we get to that point of demonstrating such a thing, we need to show it. Okay, so we have well defined. So going back to the top, you see how that worked. Sorry for the lack of space here. Is this an automorphism? Yes. Okay. So now showing that this is a homomorphism. So this is a little bit different. We want to take alpha and beta. Let alpha and beta be elements of the automorphism group of G. Okay. Not quite transitivity yet. So you can't refer to this proof. You'll have to reproduce this and put it in your own words, because I actually want to see the write-up. So if you do have a redo, I want to see you write it up and formalize it. But I'm trying to illustrate how we work this out. So you actually show this work is what we're looking to. What we just shown though is that the function's well defined. So what it means is tau of alpha is well defined. So yeah, the question was, can we refer to this as a proof of transitivity? I'm actually asking you to actually write this up because I think it's good practice for all of you, even though it might have appeared on your homework already and you have a possible rewrite. Alright, tau of alpha equals this this nice little map here. Is it a homomorphism? If we have alpha and beta in this automorphisms G, what happens here when we look at tau of alpha composed with beta? Okay. So what does that mean? Well, that means we go phi of alpha composed with beta composed with that phi inverse. And what we want to show that this equals tau of alpha composed with tau of beta. Well, it might look kind of scary right now, but we need to do a slick trick, and this one might be easier. Well, rather than do a slick trick, I'll actually go through another route. What is tau of alpha, tau of beta? Well, notice tau of alpha is phi of alpha, or phi composed with alpha composed with phi inverse, and then composition between these two, and that would be phi composed with beta composed with the phi inverse. So can we actually see how this makes a connection? So how do we make that connection back to the top piece? Well, one thing we can do with these functions is associativity. Right? So associativity, you can rewrite this as phi composed with alpha composed with phi inverse composed with phi composed with beta, and that is composed with phi inverse. Okay, this right here is the identity map. Okay, well, with that in mind, we have the identity map, and we can break this down a little bit further. This is phi, oh, don't let your eyes fool you, that's a phi right there, composed with alpha, composed with beta, composed with phi inverse. Okay, so what happens at the end of the day? Well, we can rewrite this one just exactly the same way. Just drop the parentheses. Phi composed with alpha, composed with beta, composed with phi inverse, and so tau is a homomorphism. Now, this is slightly different because before we were dealing with elements in H, and mapping to other elements in H. Now we're mapping to other functions, so keep that in mind when we're mapping from one function to the next. It gets a little bit trickier. So one-to-one and onto, we're trying to see, can we map to any old automorphism in H? So first off, let's do one-to-one. So assume, let's say we have phi of, I'll use alpha and beta again. Phi of alpha equals phi of beta. We want to show that alpha equals beta, ideally. Okay. So notice this means, I'm sorry, I wrote phi of alpha. Getting in a bad habit there. Should be tau. tau is our map. So that means we have phi of alpha, and I don't need the parentheses anymore. Phi composed with alpha composed with phi inverse equals phi composed with beta composed with phi inverse. Now granted, once again, I should probably actually have different elements than what I'm using up above, but hopefully you get the gist, and then when we write up it can be a little bit nicer. So how do we actually get rid of this stuff and whatnot? Well, notice we can take a phi inverse on the left hand side. So if I do it on the left hand side here, and let me put the composition in there. Alpha composed with phi inverse equals phi inverse. Notice I made that phi inverse on the left hand side deliberately in both cases, and we have to be careful. If we put it on one side, it has to remain on that same side. So notice now we can put parentheses here, and so we have our mapping becomes beta composed with phi inverse, and that should equal, sorry I switched sides, but hopefully you get the gist, alpha composed with phi inverse. Can you guess what to do now? Well, when you take a look, we can do another composition from where we start. So when you did phi inverse, if you did phi right back, well, like right from the get-go, we start in G, do phi, and then phi inverse. We should get, so you can go beta composed with phi inverse, and let's say we started with that new function phi, and you have alpha composed with phi inverse composed with phi, and notice that it means beta equals alpha. Alright, so what does that mean? So tau is 1 to 1. Alright, so I know we're kind of all over the page. The last component here, so we have well defined, we have all this junk. I'll try and fit it in here for onto. Let's let tornado be an element of the automorphism group of H. We want to find something that maps to tornado, and it has to start in the automorphisms of G. And that's the trick, is showing that it's in the automorphisms of G. I'm not sure if I can fit it all in here, but hopefully we can see that. So the one things that we need to do is we need to start in G. In order for us to start in G, that means we probably want to start. Now remember, this is an element in odd H. So we want some tau, a couple different ways. We'll show this actually how we did it before, so we can actually solve it. Tau of alpha equals our tornado, and that implies that this phi composed with alpha composed with phi inverse equals our tornado. Okay, so obviously this won't be the way we write up the proof, but it kind of is our work to try and get there. So notice if we reverse the order, right? So if we start with phi on the right, that gives us phi composed with alpha equals tornado composed with phi. The reason why we compose the phi with this part on the left hand side, or appearing on the right hand side of this left hand expression, the phi inverse composed with phi becomes the identity in. So basically you're left with this. Now we're going to finish with doing a phi inverse on the left. So alpha equals this phi inverse tornado composed with phi. Alright, so let's make sure that this is an element of G. So notice we start on the right hand side, you start with phi. So we start in G, we map to H, we do the tornado, so the tornado thing, it goes right here. Okay, and then we take phi inverse and we go right back to G. So this is an element of the automorphisms G. Okay. So at the end of the day, what do we want to do? Well, we notice that tau of this phi inverse tornado composed with tornado composed with phi, when we plug it in, notice you get phi composed with phi inverse, or I'm sorry, yeah, phi inverse composed with tornado composed with phi, right? All that's in the middle, and then that's composed with our phi inverse. Notice that this, you have left hand side, those two, phi and phi inverse cancels, and then you have phi and phi inverse again, those cancel, so you're left with just that tornado. And that's exactly what you wanted to show. And this basically, the last line would be how you approach a proof of this. So you'd have 1-to-1, you'd have onto, you have it's a homomorphism, and we have it's well defined. That should be the first thing we technically check. So we have it well defined. One little caveat here, you got to make sure to note that this is an automorphism of G. So you see a lot of work, but as soon as you start to understand how the automorphisms work, you're in pretty good shape in terms of how these mappings go about. And so, yeah, basically that's our big kicker in terms of automorphisms. That's one of the harder problems, but I wanted to make sure we all took a look at that when doing the homework. So, moving forward. So a new definition, let's talk about the orbits and stabilizers. So what you saw in class, the way I was kind of working with it was from a group action standpoint. And so this is more along the lines of your book, and hopefully this will make a little more sense as to what's going on. Obviously with the Rubik's Cube group, we were talking about some big old group operations. So hopefully this will let you see it in action and see how it works. So let G be a group of permutations of a set S, and then for each I and S, we have the stabilizer of I and G. It's going to be just the phi that are in that group of permutations, such that phi of I fixes I, essentially. So what keeps it at the same element? And on the other note, for orbits, if we have a group of permutations on a set S again, the orbit of I under G, so we're going to denote the notation for what your book uses is this orb G, sub G, and then you have of I, is given by everything that gets mapped to by phi, where phi is some element in G. And the big one that we like to use over and over again is groups that are generated by certain elements. So let's take a look. Let's consider the set 1, 2, 3, 4, 5, 6, and let's let G equal, and we're going to make it a cyclic group just to make it easy. We'll have this be the group of 1, 3, and then 2, 4, and 5. Okay. So just so you can get an idea as to what happens, G equals, well, first element you have 1, 3, 2, 4, 5. So those two cycles are disjoint, so we don't have to do much work. Now let's take a look at what another element might look like there. So when you compose it, notice the 1 and the 3, compose it with itself. 1 goes to, well, here, let's take a look. 1 goes to, you'll notice, 3, and then 3 goes back to 1. So that means 1 goes to 1. So I can just actually close off that cycle. Okay, so I have 1 goes to 1. Now let's start our next one. 2. Where does 2 go to? 2 goes to 4, and then I'll have to redo it for the second composition. So 4 goes to 5, so 2 goes to 5. Now where does 5 go? Well, 5 goes to 2, and 2 goes to 4. So that goes to 4. And now notice 4 goes to 5, and 5 goes to 2. So if you actually did the composition out, you get 2, 5, 4. And let's check 3, because that's the one number left. Notice 3 goes to 1. And then when you redo that, you get 1 goes to 3. So 3 would have gone to itself. And with that in mind, remember we don't write those 1 cycles in our nice little cycle decomposition there. So we have 2, 5, 4. So now our next two, so to basically do this composition 3 times, we're basically just composing these two elements right here. So let's start with 1. Notice 1 goes to itself in this element, but then 1 goes to 3. So that means 1 goes to 3. Okay, well, after that, what happens? Okay, so we have 3, oh, and I closed it off already, I should be careful. 3 goes to itself, and then 3 goes to 1, and you can see it does close off. So what about the next element? So 2, where does 2 go? Well, 2 goes to 5, and 5 goes to 2, so 2 goes to itself. So we could actually get rid of that 2. Right? And then, what happens? Well, let's check 4 would be there next on our list. So I could do 4 goes to, where does 4 go to? 4 goes to 2, and 2 goes to 4, so 4 goes to itself, and then once again we can, since it's a single cycle, you're good there. And so we can start with 5. Notice 5 goes to 4, and 4 goes to 5, so we can close that off. That's a single cycle as well. So all you're left with is 1, 3. Okay, and now for our next bit, what happens? Well, we want to compose this with our first term, or you can compose this with itself twice, whichever you prefer. So what happens? Well, notice if we started with 1, 1 goes to 3 here, and then 3 goes back to 1. So 1 goes back to 1 essentially, and so we're done with 1. We don't need to write it. So let's take a look at 2. Where does 2 go to? Well, 2 goes to itself in this one, but 2 goes to 4. So you get 2 goes to 4. Okay. Well, then on our next one, where does 4 go? Well, 4 goes to itself here, and then 4 goes to 5. So 4 goes to 5. And I wrote that back because 5 goes to itself, and notice 5 goes back to 2. So you're good there. Now for our next one, what actually happens? Let's check 3. Well, 3 goes to 1, and 1 goes to 3, so 3 is fixed. So we're good on that piece. So now, moving 2, 4, 5, composed with our first term. So notice 1 goes to itself, then 1 goes to 3, so 1 goes to 3, and then 3 goes to itself, then 3 goes to 1, so we can close that off. And where does 2 go? 2 goes to 4, and 4 goes to 5, so you get 2 goes to 5. Then 5 goes to 2, and 2 goes to 4, so you get another 4 there. And then 4 goes to 5, and 5 goes to 2, and luckily we close that off. And hopefully you're catching the trend here for this group of permutations. So what happens on our next piece? Well, let's take a look. So with this next piece, let's see. 1, 3, 2, 5, 4. And what else is left? Well, you compose this one with this one. Notice your 1 goes to 3 and 3 goes to 1. So 1 goes to itself. 2 goes to 5 and 5 goes to 2, so 2 goes to itself. 3 goes to 1 and 1 goes to 3, so 3 goes to itself. 4 goes to 2, but 2 goes to 4, so 4 goes to itself. And 5 goes to 4, and 4 goes to 5, so the 5 goes to itself. So that is just the identity, and notice we start repeating. So G is just those elements. Whew. Okay, so now where do we go from here? Well, the key component in terms of what we're doing, so we have two things that we can look at. We can look at the orbit and the stabilizer. So first off, let's look at the orbit of G of, let's say, the element 1. What does that equal? Well, what are we looking for? If you recall, we'll go back one slide here just to show you. Orbits G is, if we take any phi, we're taking in that list of elements in G, phi of I, that is an element of our orbit. So essentially we're looking at what is getting mapped to once again. So what is getting mapped to in this case? Well, notice with the identity, that's the easy, well actually let's start here. 1 maps to 3, so 3 would be the first element in here. Notice there is no 1 listed, so that means 1 goes back to itself, so 1 would be listed here. Notice 1 goes to 3 in this case, which we already have written down. One goes to itself, one goes to 3, and then one goes to itself once again. Okay? So notice we were good to go there. Okay, now let's take a look at our next bit. What's about the stabilizer in G of 1? What does that happen to equal? Well, in this case, what should we be looking at? Well, we're looking at the permutations in this case from your notation. So you're looking for the permutations in G that fixes that I. So what are the permutations that fix 1? Well, notice 1 shifts to 3 in this first element, so that doesn't fix 1. However, the second one does fix 1. Okay, so notice we have 2, 5, 4. That's an element. Okay, second term, 1 goes to 3, so that does not fix 1. Okay. This term, our 2, 4, 5, notice that does fix 1, so we can put that in our stabilizer. That stabilizes 1. And then 1, 3, since that's in there, that's not stabilizing 1. And it's shipping 1 somewhere else, so that's not in there. And then we have our E, right? So at the end of the day, what actually happened? Well, we had 2 elements here and 3 elements here. One thing to take note of: orbit of G of 1. If we take that order times the order of the stabilizer of G of 1, what happens? Well, we might be surprised to see this. So if you take the orbit, notice that had 2 elements, so this is 2 times 3. Right? Not to be confused, I did use the numbers 1 to 6. The set size didn't make much of a difference. I'm more focused on this orbit and stabilizer here. So you have 2 times 3, and notice that equals 6, essentially. Okay, I want you to see a couple more here as to what happens. What happens about the orbits of G of 2? Well, okay, now let's take a look. Where's 2 get shipped to? 2 gets shipped to 4. Okay. 2 gets shipped to 5 in this one. 2 gets shipped back to itself. 2 gets shipped to 4, 2 gets shipped to 5, and 2 gets shipped back to itself, or mapped, or whatever you want to call it. So that is our set there. What about the stabilizer? What stabilizes 2? Well, notice 2 is getting mapped somewhere other than 2, so that doesn't stabilize it. 2 is getting mapped somewhere else, so that doesn't stabilize 2. 1, 3, though, that doesn't map 2 to any other element besides itself. So 1, 3 would be an element of the stabilizer. Okay. Oh, by the way, so just so the question doesn't matter if it's 1, 3 or 3, 1. Since it's set notation, they're unordered pairs, so it does not matter. They're the same thing. So 3, 1, 1, 3, they're the same thing. If you see parentheses, though, that's when order does matter. Okay, so it doesn't matter if we write the set containing 1, 3 or the set containing 3, 1. Nope, no difference. Whatever you want to write, both the same thing. So moving forward on this one, and I was writing, I'm sorry, I wrote stabilizer of 2, or said stabilizer 2, and I wrote stabilizer 1. I meant stabilizer 2. So otherwise 1, 3 would not be part of that stabilizer. So now, if you notice, this one 2 maps to 5, so that's not in the stabilizer, but the identity is. And notice any stabilizer that we talk about, the identity is always going to be along to there. One thing I want you to take note again. Notice we had some different things happening. Oops. If I take the orbit of 2 and multiply by the stabilizer, sorry. The stabilizer of 2. Well, notice we have 3 times 2 this time, and that equals 6. Is that a coincidence? Well, let's take a look. Maybe we'll try another one that doesn't seem to appear. Notice 6 doesn't appear anywhere, right? So if we look at the orbit of 6, well, 6 doesn't get mapped to anything but 6 in the first case. 6 maps to just itself in the second case, 6 maps to itself in the third case, 6 maps to itself in the fourth case, 6 maps to itself in the fifth case, 6 maps to itself in the sixth case. So 6 just maps to itself. So 6 is the only thing in its orbit. Okay. If you look at the stabilizer, that's a G down below and this is a 6. Don't let your eyes fool you. What does that equal? Well, notice what stabilizes 6. Well, it's going to be all these elements. So that's just G, right? So in general, what happens here? Well, if we take our orbit, or not in general yet, of G of 6, the number of elements in that set times the stabilizer of G of 6, that will equal, well, notice that's going to be 1 times the number of elements in G, which is 6. So magically we always ended up with 6. Is that a coincidence? Well, no, not quite. What we have in general, there's an orbit stabilizer theorem, and that's what's going on here. So there's a theorem, and that we can make good use of too. So the orbit stabilizer theorem basically says, now granted, G can be any general group and then any set that we're looking on in any element, or it can even be a group of elements that we're looking at. But if we take the order of the orbits of G of this point I, multiply by the stabilizer of G at this point I, as long as these two things are the same, this should always equal the order of G. The only thing is G has to be a finite group of permutations, right, on a set S. So finite group of permutations is kind of important there. So keep that in mind. But for any I from NS, we can use that. So keep that in mind, and that's kind of the main theorem when it comes to orbits and stabilizers, and that's something that's going to be quite useful later on down the road. So hopefully you got some help out of this, and if you have any questions, please feel free to ask and come to class with questions. That's the main thing that we're looking for. So just come into class with questions and all that jazz. Hope you all got some of your questions and some problems answered along the way.